Thank you, sir.
So Dr. V. Reddy is very good friend of mine.
Yeah, no.
You also, whenever you come Delhi, meet me.
Yeah, sure, sir. ఇది సార్ చేసుకున్నది Sir, Ranjan sir, please switch on your camera, sir.
Camera
Video,
is
sir.
on.
Video.
Video is on. My video is on from another system, that is Dr. Kumar Rakesh Ranjan.
Okay, sir. Yeah.
Is it visible?
Yeah, sir. Now it is visible.
Okay. Because I am using two systems. On my desktop there is presentation, and on my mobile it is video.
Thank you, sir. So thank you, Dr. Ranjan sir, for accepting our invitation to give a expert talk on exegetic analysis of solar pond and desalination in the 2-week faculty development program on renewable energy intervention in industry, domestic and commercial applications. Thank you, sir, for accepting our invitation. So good afternoon to everyone. So today we have with us Dr. K.R. Ranjan, is a senior faculty of mechanical engineering from Aryabhatta Institute of Technology. So sir is ready to give expert talk on exegetic analysis of solar pond and desalination. So before starting, I would like to introduce the Dr. K.R. Ranjan. So sir is a senior faculty at Aryabhatta Institute of Technology under the Department of Training and Technical Education, Government of NCT of Delhi, New Delhi, India since 1997. So sir has completed his PhD from the Center of Energy Studies, IIT Delhi. So in the areas of solar thermal systems, and contributed more than 15 research papers on the solar thermal and other renewable energy technologies and systems in the international journals and conferences of reputed. So sir has wide teaching and research experience in mechanical engineering as well as in the renewable energy systems. So sir is also a life member of professional societies, Solar Energy Society of India, and as a member of IST also. So with this, I welcome you, sir, to give an expert talk in this session. So over to you, sir.
Thank you, Dr. V. Siddha Reddy,
Yes, sir, please, sir.
coordinator of this FDP program. And I am privileged, I am very much happy to be present with all the participants uh, from the various background. Especially, I feel maximum participants are from teaching institutions. And I am also very much thankful to overall the Rajiv Gandhi Memorial College and Engineering and Technology, Nandyal. I am very much thankful to Chairman Sir Dr. M. Shanti Ramudri and MD Sir Dr. M. Sivaram, and the Principal of this Engineering College Dr. T. Jayachandra Prasad, and Director Admin and Placement Dr. D.V. Ashok Kumar, Professor and HOD Dr. K. Tirupati Reddy, and my friend Professor Dr. V. Shiva Reddy, and other faculty members and staff of the college. I am especially thankful to Dr. V. Siddha Reddy, who is giving me such a very good platform and coordinating this FDP program. So today I am going to give my view on the topic exegetic analysis of solar pond and desalination. Dr. Reddy, is it
Yes.
audible?
Yes, sir. Audible, sir, please.
Okay. In between, you give me hint.
Yeah, yeah.
It is going on well. Otherwise,
Sure.
sometime na network problem, and a speaker used to telling, and but speaker audience is not listening.
Yeah, sir.
So,
Sure, sir.
in the mean time, you just give me feedback that it is going on well.
Sure, sir.
Uh, my dear all participants of this FDP program, I am giving you the lecture on exegetic analysis of solar pond and deceleration. First of all, I wish to explain that I am not teaching you. I am not sharing my knowledge with you. My motto, my basic view of presenting this lecture, keeping in my mind that this lecture will help your students. I assume all the participants are well qualified. You all know what is exergy, what is solar pond, what is desalination. But I have planned my lecture in such a way that this will give you an insight how to get project work done from your students on such topics, or if you are doing your research work, or you are guiding your research students, your students should think like the way I am giving you the presentation. So never mind and never think that I am teaching you. First, first of all, you keep aside the fact that I am teaching. No, I am just sharing my knowledge the way I expect any student should think about their project, think about the renewable energy, think about the just your topic renewable energy development in industry, commercial and domestic application. It is very good topic, and your complete FDP is planned in such a good manner that all the topics are covered in this FDP. and I have got one opportunity to explain about the exegetic analysis of solar pond and desalination. So now I move forward, and I I was the participant yesterday when Dr. V. Sivareddy was explaining about the all exegetic analysis of thorough solar thermal systems, solar thermal power plants, and he has explained more about the exergy analysis, and other experts before me have explained so many things. Here now I move forward. As you all know, there is concern and intervention about shortage of energy, food, and safe drinking water in the light of threats of global warming and climate change. There is demand of time to develop systems and techniques for effective utilization of available energy resources, energy conservation, and high-grade energy saving by the use of renewable energy sources, higher energy and exergy efficiency, reduction of exergy destruction in the processes and systems. Solar energy is one of the best promising options among the renewable energy sources. Solar energy has the potential of substituting a significant fraction of the current and future global energy demand without inflicting any environmental impact. It is very much important points. And then saving high grade energy by using variety of solar thermal systems for thermal applications up to 300 degrees centigrade. This lines, this line explains, I will explain it a little bit. Nowadays, and when we do not use the renewable energy sources, we use thermal application of up to 300 degree centigrade with the help of high grade energy. Means for simple heating applications, simple applications below 300 degree centigrade, we use electricity. Electricity is the high grade energy, and it has been found that there is no need to utilize electricity or another means of high grade energy for thermal applications up to 300 degrees centigrade, because up to 300 degrees centigrade there are solar thermal systems already developed and are being used worldwide to meet the requirement of solar thermal applications up to 300 degrees centigrade. So why we are wasting our high grade energy in thermal applications up to 300 degrees centigrade? So nowadays, government has emphasized, and our policymakers have shifted towards solar thermal applications for applications up to 300 degrees centigrade. It will be very useful. We will save lot of energy. Simple thing. You are not so much in the cold weather, but I am in Delhi and in northern India, everyone is heating solar water heating. Not they are
Hmm?
not using solar water heating, but they use for domestic heating, water heating, use electricity, and such heating may be done by solar thermal systems. It means we are wasting our high grade electrical energy in heating our solar water requirement up to only 40, 60, and 70 degrees centigrade. So, and in the similar fashion, there are different thermal applications which can be done with the use of solar thermal systems. So, we should, as a teacher, as a researcher, we should convince our students, or we should do research in the areas how to save high grade energy in the applications thermal applications up to 300 degrees centigrade. It means we should avoid use of high grade energy in thermal application up to 300 degrees centigrade. Next, a decisive contribution to the economic and social development of rural and remote areas which are not connected with electricity grid. The another point, in the town or metro cities where electricity is available, then we are wasting electricity in thermal application up to 300 degrees centigrade. At in the second area where there is no electricity in the remote and rural areas, they are not wasting high grade energy, but they have no energy. In such situation, in such area, the solar thermal application will be very useful for the economic and social development. Dr. Reddy?
Yes, sir.
Audible?
Hello.
Audible, sir.
Audible, sir.
Okay, good. Next, capability to substitute the consumption of energy generated through nuclear or fossil fuel even in the urban areas. We have made up our mind to save high grade energy for thermal application up to 300 centigrade by substituting solar thermal system. That's another point. We are going to utilize solar thermal systems in rural and remote areas which are not connected with the electricity grid. And then the solar thermal system has capability to substitute the consumption of energy generated through nuclear or fossil fuels even in urban areas, because in urban areas also we can substitute the consumption of energy. Next, scientific communities are trying to overpower the limitation of solar energy collection, storage, and utilization for domestic and industrial applications. The conventional performance evaluation of solar thermal system is based on the first law of thermodynamics, that is energy analysis alone, and that is inadequate. Here now, our uh, our introduction has come on the point to whatever solar thermal system are being used, those systems are analyzed on the basis of first law of thermodynamics, that is called energy analysis. But that is not sufficient. A more meaningful evaluation must include second law analysis, that is called exergy analysis, which can give better understanding of the system. The second law of thermodynamics asserts that energy has quantity as well as quality, and actual process occur in the direction of decreasing quality of energy even if quantity of energy is conserved. Exergy efficiencies do provide measures of approach to ideality, and exergy losses do provide measures of the deviation from ideality. The aim of any exergetic analysis is to detect and evaluate quantitatively the effect of irreversible phenomena which increases the thermodynamic imperfection of the considered process. Exergy analysis identifies sites where exergy destruction and loss occur and categorizes their significance in order. This fact, as a researcher, we should keep in our mind. Why? we are doing exergy analysis? What is the need of exergy analysis? Because exergy analysis identifies sites where exergy destruction and losses occur and categorizes their significance. Even that can be evaluated how much exergy destruction is being made in in any process. Because energy, when we do energy analysis, there is no measurement of such type of destructions, exergy destructions. We all know as far as energy is concerned, energy is transformed from one form to another form. There is no destruction, but efficiency is low of an energy efficiency of low of any system is low. Our objective is to increase the energy efficiency. We do all efforts, we take all measures in the design, but we cannot increase the efficiency of any system, energy efficiency of any system up to after a certain limit. Why? Because in our energy analysis, we cannot detect the areas, the place, the sites where exergy distractions were taking place or are taking place. It is only exergy analysis which identify the site where exergy destruction and loss occurs. When we talk about the exergy destruction, it means we are talking about the quality of energy destructions. We will discuss in detail about the quality, but at this point, only one thing I would like to share that what is the quantity and quality. Just take one example. If we are talking about the energy of 100 megajoule, for example, 100 megajoule, that is the quantity of the energy. And that 100 megajoule will be converted into and transferred to the system, and for maybe 50 megajoule is utilized and 50 megajoule is lost to the atmosphere. No problem. If 50 megajoule is lost to the atmosphere, then our efficiency of the system, energy efficiency will be system the half, 50%, because from 100 megajoule, we have lost 50 megajoule and we have utilized 50 megajoule. So energy efficiency is only 50%. Even we find the all 50 megajoule has not done the effective work. We have not utilized 50 megajoule effectively, because as per the second law of thermodynamics, in the conversion of 50 megajoule to the work done, there will be some heat losses that is the required for the second law of thermodynamics, and that loss or even different types of losses will occur within the systems, which cannot be identified by energy analysis. It is the exergy analysis which can find those or which can calculate those exergy distractions. So now I will move forward. This information can be used to design solar thermal system also, and even here since we are talking about the solar systems, that is why I have written this information can be used to design solar thermal systems. Otherwise, this exergy analysis can be utilized in all the energy systems. Recently, this exergy analysis is not only used in energy systems, it is being used in even our educational systems, in the hospital systems, how the efficiency of such systems can be increased. But today, at this time, we will focus only on the design of solar thermal system. That is why it is written here. This information can be used to design solar thermal systems, guide efforts to reduce sources of inefficiency in existing system. During the past decade, exergy-related studies have received tremendous amount of attention from various disciplines ranging from chemical energy engineering to mechanical engineering, from environmental engineering to ecology and so on. That is why I was talking about our different use of the exergy analysis. But the application of exergy approach to the renewable energy system, especially on the solar thermal system, may be considered at an early stage. Now, solar thermal application in the temperature range of up to about 120 degrees centigrade are designated as low grade heat application. When I started lecture, I was talking about the solar thermal applications up to 300 centigrade. Now we are confining ourselves to up to 120 degree centigrade only, because between 120 and 3 degree centigrade, such applications are like the solar thermal power plants. And if we leave solar thermal power plant to be analyzed by so many experts, I am confining myself up to 120 degree centigrade only. So for any teacher, they can teach their students with the division, with the classification of solar thermal systems like this. Solar thermal applications in the temperature range of up to about 120 degrees centigrade, or solar thermal applications in the temperature range of above 300 degrees centigrade. So this differentiation divides solar thermal applications in different categories. The solar thermal application in the temperature range of up to about 120 degrees centigrade are solar water heating, solar air heating, heating of swimming pool, distillation of water, solar cooking, space heating and cooling, solar greenhouses, crop drying, a small scale thermodynamic conversion of heat into mechanical power and electricity. That is a small scale, not large scale. Large scale thermodynamic conversion of heat into mechanical power and electricity will come under the areas of temperature range above 120 degrees centigrade up to 300 degrees centigrade. Then next is process heating of many industries such as dairy, food processing, chemical and textiles. In the present discussion today, the following solar collection storage thermal system for low grade heat application have been selected. Salt gradient solar pond as solar collector cum storage, that is, it is also called simply solar pond. Basically, solar pond is salt gradient solar pond, and that salt gradient solar pond is solar collector cum storage system. In solar pond, there is both type of works is being done: solar collector, solar collection and storage. The another system we will discuss in brief about the passive solar distillation system, and third one I will try to explain if time will permit, that is about the active solar distillation system integrated with solar collector or solar pond. Now, I hope and assume that almost all participants are familiar about the solar pond. But from the point of view, as I earlier told all of you, that I am not teaching, I am giving you one way how to attract your students about these solar systems, especially solar thermal systems. So for the students' point of view, they should know what is solar pond. As the name suggests, pond is a collection of water. But when we talk about the solar pond, design of the solar pond, analysis of the energy and exergy of that solar pond, that is artificially constructed pond. It is not natural pond. Our system, solar pond being described here, is an artificially constructed pond in which significant temperature rises are caused to occur in the lower regions by preventing convection is called solar pond. In the natural pond, there is no convection seizure. There is natural convection. So in, in natural convection, when solar energy fall on the surface of the water, it goes up to the lower regions, heat up, and after heating, it the water current comes out outer surface, and in such way the natural convection starts. So there is no rise in temperature of the natural pond very much. Due to the natural convection, there is no rise of water that can be utilized as the solar thermal mass. The one of the most simple, cost effective and commonly used solar pond is the salt gradient pond. Why salt gradient pond? To seize the convection current. In the natural pond, in natural solar pond, there is no salt gradient. The quality of water at the top, in the middle, in the bottom is same, simply water. So there is natural convection. But if we design the solar pond in which there are 3 layers of the water by mixing salt, that I will explain later on, and that type of pond is called salt gradient solar pond. Salt gradient solar ponds were not invented, they were discovered. The phenomenon was first observed in Romania in the early 1900s. Since then, the solar pond technology has passed through development phases. Today, it has reached a state of the art state incorporating all best possible improvements, making it technically as well as economically feasible for commercial application. This is a schematic of 3 zones model of salt gradient solar pond. When earlier I was talking about the 3 layers, we design the salt gradient solar pond in such a way, the topmost, it is upper convective zone, then non-convective zone, and in the lower portion it is lower convective zone or heat storage zone, HSZ. There are 3 zones, UCZ, non-convective zone and lower convective zone. This is the top surface of the solar pond, and solar energy is incident on the upper convective zone, and it is transmitted by this upper surface and reaches up to the lower convective zone, and in this zone water is heated. I will explain the mechanism later on. First, only I want to introduce you the system here and how it the water is heated. I will explain later on. So here in the lower convective zone, there is higher temperature of the water up to 90 degrees centigrade, and that that temperature is utilized by the heat exchanger, and we get the hot water. Direct hot water from the lower convective zone is not passed through this pipe. Here the heat exchanger are employed, and the heat of the heat storage zone is used to heat the water inside the heat exchanger, and we get output hot water from this way. And this is the at the upper point there is input water also, because after certain time water is evaporated, some loss of water in quantity. To compensate the loss of water, water is fed from the upper side. Yes. And now the mechanism of solar energy conversion and storage as thermal energy inside the solar pond. It is very important to know about the amount of solar energy incident on the upper surface and its reflection, absorption, and transmission through water at different zones and different conditions of the solar ponds. A part of the incident solar radiation is reflected back from the top surface, while most of it is transmitted through the top surface of the upper convective zone. It is necessary to know all these things, because based on this idea, the fact, we will able to analyze on the basis of first law of thermodynamics and second law of thermodynamics, how much energy is transmitted, how much energy is absorbed, how much solar energy is transmitted. So when we will know the mechanism of the solar radiation's transfer, solar energy conversion, then we can calculate the quantity of energy and quality of the energy at different stages. So it is that is why it is told here, it is very important to know about the amount of solar energy incident on the upper surface and its reflection, absorption, transmission through water at different zones and different conditions of solar pond. A part of the incident solar radiation is reflected back from the top surface, while most of it is transmitted through the top surface of the upper convective zone. Next, the upper convective zone is typically a thin layer of about 0.1 to 0.3 meter of nearly saltless water, in which there is vertical convection current due to wind and evaporation. The fraction of the transmitted radiation is first rapidly absorbed in the upper convective zone. However, this absorbed heat is lost to the atmosphere by convection and radiation heat transfer due to evaporation from the pond surface. The remaining radiation is subsequently absorbed in the non-convective zone and the heat storage zone before the rest of the radiation reaches the bottom of the pond. The non-convective zone is much thicker, having downward positive salt concentration gradient. Depth of non-convective zone is more than half of the total depth of the solar pond. The thickness of the non-convective zone depends on the desired temperature in high convective zone to meet the requirement of the load. Solar transmission properties, thermal conductance of water, and cost. The rate of variation of collection efficiency of solar pond is less with depth of the non-convective zone. A pond of about 1.6 meter thickness of non-convective zone may represent a better compromise in terms of lower initial cost, but having a collection efficiency about 90% of the optimum value. It is an insulating layer, reducing the heat losses in the upward direction from the heat storage zone. In the high convective zone, heat storage zone, or lower convective zone or bottom layer, the absorbed solar energy is converted to heat and stored as sensible heat in high concentration brine, where both the salt concentration and the temperature are almost constant. Its depth is typically 1 to 2 meters depending on the thermal energy storage requirement. Since there are no heat losses by convection from the bottom layer, the temperature of this layer rises substantially. If heat is not extracted, hence it becomes necessary to withdraw heat from heat storage zone for various thermal applications and to prevent boiling of water. The bottom here, the word is to prevent boiling of water, because in the heat storage zone, we have to design in such a way that the water temperature should not rise above 100 degrees centigrade, because if it rises 100 degrees centigrade, there will be the convective currents, there will be steam generations, and that steam generation will spoil overall construction of the solar pond. So it is necessary to extract heat from heat storage zone. Even if there is no need of heat, even though we will have to extract heat from heat storage zone for our applications. The bottom of the pond is usually lined with blackened plastic film made of low density polyethylene, high density polyethylene, or woven polyester yarn and Heflon reinforced nylon mesh. It prevents leakage and absorbs maximum solar radiation that reaches the bottom. All these things are available in the literature, but I am only just giving you the glimpse so that later on I can explain the energy and exergy analysis, because if we do not discuss about the different zones and how the solar energy is transmitted from the top zone to bottom zone, we will not be able to analyze it energetically and exergetically. That is why it is necessary to be explained here. Now this is the history. Uh, in You may say that is it used in India? Yes, technical and economic viability of solar pond technology in the Indian context is demonstrated by constructing and using a 6,000 meter square solar pond at Bhuj in India in the premises of a dairy plant. By supplying process heat, the pond attained a maximum temperature of 99.88 degrees centigrade under stagnation. The solar pond have all potential with the annual collection efficiency in the range of 15% to 25% to perform well for all locations and can supply adequate heat even in regions near the Arctic Circle. So here I wish to show you one video available at the Terry site about the Bhuj solar pond.
Is a paper presentation, partial presentation, quiz,
Dr. V. Siddha,
sir.
I am going to uh, show you one video on the solar pond.
Okay, sir.
Okay, sir. Okay, sir.
Sir, no voice.
హలో సార్, నో వాయిస్ సార్.
సార్ మ్యూట్ అయినట్టున్నాడు.
చూస్తున్నాను సార్, అదే అర్థం కాదు సార్. సార్ అది సార్ది ఇది పోయింది సార్, ఇది హెడ్ ఫోన్స్ ఉంటాయి తీసేసినట్టు సార్, మైక్స్ లేవు సార్. సార్ మైక్ లేదు సార్.
అదే
సార్ మళ్ళీ ఒకసారి కనెక్ట్ చేసి చేయమంది సార్, వస్తుంది సార్.
I am showing you from my mobile.
సార్ నో వాయిస్.
Just trying. Sound is coming?
No sir.
Hello?
No sound. Ranjan sir, no sound coming.
సార్ రావడం సార్.
Sir, audio not coming, sir.
సార్
నమస్తే అన్న, అది మన ఇచ్చిన చెక్ పైన ప్రిన్సిపల్ సార్ సైన్ ఏదో దాంట్లో చూపించడం లేదంట. మొన్న చెక్ ఇచ్చినా కదా 8 లక్షలది, అది ప్రిన్సిపల్ సార్ సిగ్నేచర్ దాంట్లో టాలీ కావడం లేదంటున్నాడు. వాళ్ళు ఎక్కడో మొత్తం తీసుకుపోయినారు కదా, మొన్న ఇచ్చినాము. అవులే, అంటే వేరే సైన్ ఏముంది?
Doctor, please make me host, because my system is asking only host can share the video. Is it possible for some time?
Sir.
Okay.
Yes,
okay.
Sir.
Okay.
Yes, sir. Yes, sir.
Now I am sharing.
Sir, sir.
ఒక నిమిషం.
హలో సార్.
ఉపేంద్ర చెప్పు.
సార్ కోర్స్
సార్ నా?
అవును సార్, ఇంకోటి అని చేయండి సార్, కోర్స్ చేయండి సార్.
హోస్ట్ చేసిన
హోస్ట్ వద్దు సార్, మరి మన కష్టం ఏదో సార్, హోస్ట్ అంటే ఆయన పోతుంది.
డాక్టర్ కుమార్ రాకేష్ రంజన్.
ఉపేంద్ర?
Another assistant, Dr. Kumar Rakesh Ranjan.
ఉపేంద్ర?
ఆయన వచ్చేసి మన కాన్ఫరెన్స్ అట్లా మనం వచ్చేవాళ్ళు మిమ్మల్ని వచ్చేవాళ్ళు మన కాన్ఫరెన్స్
నంబర్ ఏదబ్బా? అర్థం చేసిన
atmosphere అంటే మనకు ఆక్సిజన్ సేవ్ అవ్వదు. and మనకి
నువ్వు పోవస్తున్నావు
నా పోస్ట్ చేయాలి ఆప్షన్ అందుకోసం ఆప్షన్స్ రావాలి.
అలాగే
Bars of the sun have made it for thousands of years
Alright.
the object of terror, worship, and even intrigue. Although this source of seemingly inexhaustible energy has been the object of intense study since man's thought processes first evolved, it's only since the turn of the century that efforts have been initiated to tap this source. Our story today deals with a water body, a pond that will entrap solar energy. Another step in man's struggle to harness non-conventional sources of energy for the future. The need to harness non-conventional energy sources has become imperative in the face of fast depleting fossil fuels. Among the various methods applied to harness the sun's energy, the solar pond technology seems to be a promising alternative. The recently constructed solar pond at Kutch Dairy in Bhuj is the largest operating solar pond of its kind in the world. Developed by Gujarat Energy Development Agency in collaboration with TERI and Dairy Development Corporation, solar ponds have the unique ability to entrap and store the sun's heat energy for months together, even during adverse cloudy season. And this is a distinct advantage over other methods of solar collection. By Israeli scientists way back in 1958, this concept of solar pond is inspired by nature. In natural ponds, the sun's heat energy radiates to the bottom of the pond and heats up the water. The heated layer of water at the bottom, being lighter than the upper layers, rises to the surface of the pond, creating a convective motion and subsequently loses atmosphere. Usually, seabed has higher salinity. The water temperature is warm. The salt gradient solar pond uses this phenomenon of entrapping heat energy. It consists of 3 zones. The lower convective layer with a specific gravity raised 1.9 by concentrating common salt at the bottom. The middle layer with a gradient of salinity, and topped by the upper convective layer of almost fresh water. To suppress wave formation due to wind, wire nets are installed every 10 meters. As a result of this special construction, the heat from the sun is retained at the bottom of the pond. This is because the lower layer is denser than the upper layers, and the convective motion is thus restricted to the lower region. It takes about 30 days to raise the temperature of the lower layer to 70 degrees Celsius and even as high as 90 degrees Celsius. The hot brine pumped into the heat exchanger vaporizes the liquid furon, and with the resulting pressure, a turbine is run. This can be used to produce electricity and for processing heat applications like desalination and refrigeration. The renewable nature of this energy makes solar pond a viable proposition for the future.
room. Now, there was some delay in the video play.
Sir Ranjan sir.
Yes, sir. Yes, sir.
Sir, can you please make me host RGM HOD?
No, you are going to. I am making you the host. RGM HOD. Actually, my son is helping in managing all the things. He is class 7. He is in class 7.
Okay.
Normally, I use the other Google Meet for my online class.
Okay.
I am not used to on the Zoom. Here everyone is using Google Meet for the. Now you are a host?
Yeah, now okay, sir. You continue.
Okay, okay. And now I will move towards the solar desalination. This is the first part of our lecture is for the introduction of all these things, solar pond, solar desalination, and then in the later phase we will explain about the energy analysis and exergy analysis, because I know in the calculation part or the design part, no, maybe many participants will not be so much interested. So first of all, that is why I have tried to show you all the basics of the solar ponds, and now I am going towards the solar desalination. Fresh resources, as you know, are inadequate in nature. Only 3% of the global volume of the water is suitable for agriculture, industrial, and drinking purposes. There is shortage of fresh drinking water in remote and rural areas of many countries. People are unable to use popular desalination devices to get fresh water due to limited or even no supply of grid-connected electricity. Most of the desalination technologies are based on energy from fossil fuels. Therefore, there is dire need to find some desalination systems operating with locally available renewable energy sources. In the present circumstances, utilization of solar energy for desalination shall be the best solution for rural areas. It is a proven technically feasible low carbon technology, but the initial cost of device to intercept and use the low density, low grade solar thermal energy for distillation is high. It has become essential to design solar distillation system of higher energy efficiency, minimizing thermal losses and irreversibility in the components to make it technically as well as economically feasible. The solar distillation system are primarily categorized as passive and active system, as you all must be knowing about the categorization of solar distillation system into passive and active. Just I only want to throw light on it. The most conveniently used solar distillation system consists of simple passive solar steel, where the solar collection and distillation process take place within the same equipment. It is very simple in design and easier in fabrication at lower cost. We will analyze our uh, system, this only system, simple passive solar system. The active solar distillation system comprises of an additional source of feeding the thermal energy into the basin of passive solar steel to increase the evaporation rate and continue the distillation even in the absence of solar radiation. The additional means may be solar collectors, solar ponds, or waste heat available from various industries or power plant. In this lecture today, we will connect this solar simple passive solar system with our solar pond, and we will analyze the system active solar distillation system with the solar pond. Now, passive solar distillation system, among various distillation technology, as you know, distillation and membrane based techniques, solar distillation using solar stills are the simplest and economical, as it has been explained earlier. A single effect basin type horizontal passive solar still is found to be comparatively cheaper. It is also simply designed, easier to construct and operate with minimum of repair and maintenance. It comprises of three main components: metallic basin liner, saline water, and glass cover, as shown in figure in the next part. It operates on the basic principle of evaporation and condensation, similar to the phenomenon of natural raining, but within a confined space. It relies on the distillation process to remove fresh water from saline or brackish water. Solar distillation, I can show the video, but I will show it later on because it will disturb our whole lecture. This is the schematic diagram of a single effect, single basin horizontal passive solar still, showing the mechanism of major energy transfer. Uh, this is the glass cover on which incident solar radiation is you are seeing, and then the condensation takes place inside this glass cover, and distillate is collected here, distillate trough, and this is lined water in the basin, and in the lower portion this is the insulated bottom, and on this insulated bottom there is basin liner where the solar energy is absorbed, and that absorption increases the temperature, and due to increase in temperature of the saline water, the water is evaporated and it is condensed. It starts condensing on the back of this glass cover, and after condensation the distillate is collected. In this, in the this any type of this solar still, basically the brine water or dirty water, water with high salinity is kept here, and with the use of simple solar energy. No, there is no need of any electricity or any another system, just like our raining system. Just like you assume that water is here and it is heated and it is condensed below this glass cover, and condensation take place, and the distillate pure distilled water is obtained here, and in this way the saline water can be made potable water, drinkable water in the areas where there is no electricity, there is no other means of uh, uh, cleaning or converting saline water into drinkable water. This single effect basin very. Now we move upward. It has mainly three components, as I have told earlier: basin liner, that is collector, and it absorbs solar radiation and transfer heat to saline water body, and transparent cover, which produces greenhouse effect situation and also condenses the vapor evaporated from saline water. A number of parameters are responsible for the performance of solar still. As from the description, we can find that it is very simple. But when we are going to analyze mathematically, energetically, exegetic analysis, then it is not so simple. There are so many conversion of heat and mass transfer, we will have to make it in the equations and calculate the different at the different point heat transfer, quality, quantity of energy, then make the energy balance equations. We will discuss in detail later on. So, and a number of parameters are responsible for the performance of solar steel, in which amount of solar radiation available, depth of saline water in the basin, and consequently temperature of evaporating surfaces, wind velocity, and ambient temperature are very important. All these factors are very important because all
Hello.
these factors will come in picture when we will frame the energy equation. Other key design parameters are material of basin liner, transparent cover, materials and thickness of insulation, inclination inclination angle of glass cover, and orientation of the solar steel. In any solar thermal systems, any solar systems, orientation of the system is very important. In a passive solar steel, the higher fraction of solar energy is absorbed by the basin liner and is the only sources of energy to raise the saline water temperature. It limits the rise in temperature of saline water body, leading to lower productivity. Another cause of lower productivity is due to non-productive period after sunset and in cloudy days. Many varieties of passive solar steel have been designed and operated to enhance the productivity and efficiency in the last few decades. This condition, when when it becomes non-productive due to no sunshine and in cloudy days, in such case the active solar steel plays a major role. The reported energy efficiency and distillate output per unit area of the solar steel is found to be low in the range of 30 to 45%, and with less than 5 liter per meter square per day of fresh water production for most cases, even under optimized operating conditions. A new approach to enhance the productivity of a solar steel by introducing an additional basin in the double slope solar steel is attempted. Maximum productivity has been found to be 5.68 liter per meter square per day for double basin solar steel. In way back in 1973, Cooper has calculated and observed that the theoretical and experimental maximum efficiency of an ideal single effect solar steel can reach up to 60% and 50%. Theoretical and experimental. Theoretically, it can give you the efficiency, energy efficiency up to 60%, and experimentally, the energy efficiency may be up to 50%. But we are not reaching at this level now. Even now, it is the ideal. Just like our Carnot cycle, in the case of the solar steel, Cooper has given that maximum limit. He has calculated, and there are actually based on his observations and calculations after Cooper, there are so many papers, and based on all those equations, uh, the solar steel of different types have been designed and being used nowadays. Solar steel is not only in the paper and in only research paper. Basically, solar steels are being utilized also. There is much scope now from the research point of view. We should know there is much scope to improve the performance of the actual solar steel to bring it at commercial stage. It may be possible by increasing distillate production, utilizing maximum solar energy available without increasing the expensive solar energy collection area. That should be our goal, because if we increase the solar collection area, naturally productivity will increase, but the cost will become very high. So our objective should be in during the design, without increasing the expensive solar energy collection, how the productivity can be increased. It can be increased by the effective energy utilization. And if we talk about the effective energy utilization, then the matter of exergy analysis come in the picture. The results show that the maximum shows that between 19 to 26% for a triple effect system, 17 to 20% for a double effect system, and less than 4% for a single effect system. It is of this effect system. There are different way of the system. That just I have shown you the picture. It is single effect solar steel. The another system is double effect, triple effect system. All these things are available in the literature. You can see, just I am giving you the glimpses of it. It is observed that double slope solar steel gives higher distillate output in summer with low annual distillate, higher exergy efficiency, low cost of production, and low energy payback time is compared to single slope solar steel. Various improved designs of the passive solar distillation systems are suggested and tested for increasing the efficiency and productivity by researchers. Special solar steels have also been designed for specific purposes like wars, expeditions, voyages, etc.
Sir
Now
Ranjan
the
sir,
third part, yes.
sorry for the disturbance. So one participant is asking the question, what is
Okay.
meant by triple effect system?
Actually, first of all, we should know the single effect. In the single effect, we have seen that the condensation took place on the glass cover. But in the double effect and triple effect, this distillation takes place at different points. We will explain it in later on. So, if when I will explain my lectures, so maximum queries will be solved.
Okay, sir, please.
Okay. Now the third part is active solar distillation system integrated with solar collector. Many modifications have been made to improve the performance of the solar steels. One of the arrangement is the integration of solar collector. Earlier, I have told you the limitations of the sunshine duration can be met by incorporating passive solar steel with any active system. Active system means mode means inclusion of some mechanical means, another means of energy other than solar energy. One of the arrangement is the integration of solar collector with passive solar steels to operate in the active mode. In such cases, the temperature difference between the evaporating and condensing surfaces are increased by feeding the additional thermal energy. This additional thermal energy comes from the solar collector or solar pond to the basin water of solar steel. And in such case, even there is no sunshine, the solar distillation take place. The effect of increasing the number of flat plate collectors in case of active solar distillation system has also been observed. A few work on thermal distillation by salinity gradient solar pond have been reported in literature, and the one very good author and researchers, Calagrew, has suggested the use of salt gradient solar pond to operate a low temperature distillation unit for freshwater production. Integration of a mini solar pond with a solar steel has been developed by Sridhar and Veluruguna in 2007, and it is available in the research paper. Active solar distillation system, then here lower productivity is the main limitation of the passive solar distillation system. A number of studies has been carried out to solve this problem. It has been established that the daily freshwater production of passive solar steel can be increased significantly by increasing the temperature difference between the evaporating surface of saline water and condensing surface, that is transparent cover. This condition can be achieved either by increasing the temperature of the saline water body or decreasing the condensing surface temperature, or by the combination of both. Active solar distillation systems are developed to accomplish the task of increasing the temperature of saline water. This is the basic aim, because when the saline water body temperature will rises, there will be more evaporation here through some external sources of thermal energy in addition to usual incident solar energy on the solar steel. The model integrated system comprises of a single effect basin type single slope passive solar steel in which external thermal energy is fed from a nearby salinity gradient solar pond capable of generating heat for various low grade thermal application for the entire years, even during cloudy days and off sunshine hours. This active solar, the model we are going to discuss here, our solar system, solar distillation system is uh, added with the solar pond. Today, an active solar distillation system integrated with salt gradient solar pond is proposed and studied based on energy and exergy. It is yet to be tested experimentally. This model, when in which the we have made the active solar distillation system, it is theoretically analyzed based on energy and exergy. It is not tested experimentally. So it will be a very good work by any researcher to start work on it. They can design and develop this system locally and calculate the productivity of the distillate, and it can be compared with our results. So any participants who are interested for the PhD work, research work, they can do work on this model which we have developed. It has not been developed and theoretically earlier. It is not available in the research paper. It is the only our research paper that is published for this type of models. This is the model. This is the solar pond, and it is connected with the solar steel, and solar now it can be called the active solar distillation system. If we uh, delete this portion, solar pond, only solar steel is there. This solar steel is passive solar steel, but if it is connected with the solar pond, it becomes the active solar distillation system. In the present model of active solar distillation system, it is assumed that the passive solar steel is integrated with solar pond with the help of a heat exchanger, which transfer heat of the solar pond at constant temperature to the saline water body inside the solar steel. It facilitates to increase the evaporation rate and production of distillate even during off sunshine hours in active mode. This integration is different from the combination tried by other researchers using various types of collectors, mini solar pond or shallow solar pond. Various researchers have worked on it, but it is entirely different from their works. In all the reported combinations, saline water is heated in the solar collector system implied in the experimental setup. But in the present model, there is no flow of saline water. This is the unique things. It is not circulated for heating in the heat storage zone of the solar pond integrated system. Only heat is transferred to the basin water through a heat exchanger, not visible in the figure, and saline water is heated in the basin itself. There is no interconnection between the water levels. Only heat is taken from the pond and is fed to the solar steel. In all other research work, it is not done. During sunshine hours, the saline water is heated both directly by solar radiation and indirectly through solar pond, but during off sunshine periods, only indirect thermal energy is provided. A water pump is also required to circulate heated water in the heat exchanger integrating solar pond with solar steel, but the power consumption to run the pump is neglected here. The connecting pipe is perfectly insulated to minimize thermal losses, assumed negligible, from the hot water flowing through pipe to the atmosphere. The capacity of solar pond is large enough to supply heat to a large number of solar steel. It is another thing, very important thing. With the help of this solar pond, we cannot, not only single solar steel will operate, but we can add a large number of solar steel in parallel to increase the volume of fresh water production to meet the demand of community, hotels, hospitals, railway stations, or even airport on commercial scale. This is the beauty of this model. So I will be happy if any at least 1 or 2 participants starts working on it. At the same time, thermal energy need for other applications such as building or process heating and power generation using organic Rankine cycle can also be fulfilled in addition to desalination from the same solar pond, because solar pond has a huge capacity. So a small portion of heat may be utilized for desalination, and the rest heat can be used for building or process heating and power generation using organic Rankine cycle. This integration may be treated a part of hybrid system based on thermal energy supply from a solar pond. Solar pond is found to be suitable to supply thermal energy in various thermal desalination processes on large scale. A proper integration of solar thermal energy can reduce the utility cost and the environmental impact. The proposed integration is also likely to be cost effective cost cost effective and environment friendly. One participant have asked what is the maximum volume of fresh water production by using solar power. It will take time because on the system there is internet disruptions.
Okay, okay, sir.
It is connecting now.
Okay, okay, sir. Sure, sir.
My presentation may not be visible to you.
No, no,
Not
sir.
visible, sir.
Yes, yes. There is internet disconnection.
Yeah, you can start explanation, sir. No problem.
Yes, yes, yes. To whom I am talking?
Surety.
Already.
Yes, yes. Voice is resembling. Uh, and you have explained maximum thing of exegetic analysis. Now I am moving towards that.
Okay,
Earlier
okay.
I have explained about the systems, because without systems, because many participants are not very much interested in the theoretical calculation.
Yes, sir.
So
Yes, sir. No.
I tried to explain the systems, schematic diagrams, and mechanism of heat transfer in the solar pond and solar steel. Now
Yes,
I
sir.
am moving towards the exegetic analysis.
Yes, sir.
Your area. I am entering into your area.
Okay, sir. Zoology
A
area,
number
sir.
of work are available on thermodynamic analysis of solar thermal system for water heating and distillation based on energy analysis. Limited and simple studies available on the exergy analysis of solar water systems, salt gradient solar ponds, and solar distillation systems. Salt gradient solar ponds are operated successfully what uh, uh, you can start my video because host has disabled it. So because I am sharing from the mobile, so you can see my face also.
Yes, sir. Salt gradient solar pond are operated successfully in India, as I have shown you the video also. Please wait for 1 minute. No, I am just only explaining from mobile because there is internet disruption. Is it audible?
Yeah, sir. Audible.
Is it audible?
Sir, audible, sir. Please go ahead.
Okay. I will share my this PPT with you so you can give the participants
Okay, sir.
later on.
Okay, okay, sir.
Yes. The another thing is know about the thermodynamic basis of solar thermal radiation and exergy analysis. Earlier, whenever we talk about the exergy, we talk about the exergy of in terms of heat, normal heat. But the exergy of solar energy is different. Solar radiation is the renewable source for the working of all solar energy devices and systems. The maximum work producing potential of solar thermal radiation has been the subject of intense research activity. This part of lecture discusses the fundamental concepts of thermodynamics, thermodynamics of solar thermal radiation, and energy and exergy analysis. This basic knowledge is used to carry out the energy and exergy analysis of solar collection storage thermal system for water heating and distillation. Exergy is the part of energy which is useful and therefore has economic value and is worth managing carefully. It provides a lot of opportunities for improvement. Exergy is a property of the system environment combination and not of the system alone. At the dead state, that both the system and environment possesses energy, but the value of exergy is zero. Exergy can be defined as the maximum theoretical work obtainable from the combined system of the system plus environment as a system passes from a given state to the dead state while interacting with the environment only. Available work from heat is evaluated as exergy is equal to maximum work is equal to Q, that is heat energy, in bracket 1 minus T0 by T, where T0 is the energy temperature of the environmental condition, and T0 by T is the temperature of the system. Exergy is consumed or destroyed due to irreversibility in the process or components. For the steady flow process, exergy destruction is given by exergy destruction or irreversibility is equal to maximum work minus actual work, and it gives you the work lost, that is the exergy destruction. The exergy balance for any system or its components can be obtained by combining the conservation of law of energy and non-conservation of exergy. That is exergy input minus exergy output. Exergy output means useful and or losses
minus exergy destruction equal to exergy consumption or distractions. And now the exergy efficiency that is now it is visible.
Yeah, sir, visible.
Exergy efficiency is equal to desired output by maximum possible output, that is called exergy output by exergy input, and that is equal to 1 minus exergy destruction or irreversibility by exergy input. Here now the in this equation exergy is equal to W max, we find Q. Q is the thermal energy, thermal heat, but this thermal heat will be applicable when we heat the water. But
Last
when
one.
we talk about the thermal energy of solar radiation, this definition, this formula of exergy do not work. This is the main important thing every researcher should know, which or any teacher, any faculty members who want to teach their students or guide researchers about the exergy analysis of solar thermal systems. Exergy of simple thermal energy and exergy of solar energy are different. It is main thing you should know about it. The earlier many persons, even very renowned persons, have done mistake, and that mistake has been brought into the notice of the researchers, and now they are distinguishing both type of exergy, exergy of thermal energy and exergy of solar energy. So in the analysis of solar thermal system, we will utilize two basic energy equation, exergy equation. One exergy equation you are seeing on the screen, EXQ equal to W max equal to Q in under the bracket 1 minus T0 by T. It is very simple thing, but it plays a very major role when you publish your paper, and the researchers worldwide will find that you have done some mistakes. So please be very careful in selecting the equation when we are going to analyze our system exergetically. So this exergy equation is for the thermal energy generated, and the thermal energy or energy in the solar radiation, their exergy value will be calculated by different equation, which I am going to show you. And it is not,
Sorry for the interruption.
yes.
There is a question from the participant. What are the novel things we can able to found in solar still in order to produce large quantity of fresh water?
Yes, large quantity of fresh water can be produced by active solar distillation system only, not only passive. That is why the integration of solar pond, solar collector is being used. A simple solar passive distillation system cannot give higher than 5 to 6 liter per day, but there is more requirement of distillate output, so there will be need of the active solar distillation system for the commercial level. But for domestic level, simple solar passive distillation system may work. We may use 1 or 2 solar steel for our domestic work. That will be sufficient.
Thank you, sir.
Okay.
Please go ahead, sir.
Next, when what we were talking about the difference of the exergy of the normal thermal system and the thermal radiation. So thermal radiation, because the thermal energy getting from the heated object, and thermal radiation basically from any heated object there is thermal radiation. So we are entering in the area here, the solar energy. So the thermal radiation, that is 0.200 micrometer, includes a portion of the ultraviolet radiation, the entire visible radiation, and infrared radiation. It is extremely important and most interesting radiation as it is responsible for the heat transfer. It is relevant to many domestic, industrial, and agricultural heating, cooling, and drying process, as well as to the energy conversion methods and involve fossil fuel combustion and solar radiation. The present discussion is limited to the consideration of thermal radiation, which is sometimes simply referred as radiation. After 1960, gradually interest grew in the areas of exergy of thermal radiation. Petela, this name every researcher should know. Petela has derived the emission exergy of a black surface, and the, this scientist Petela has given all the basic things for the exergy analysis of solar systems. But researchers do not sometimes they do not take his formula and calculate the solar exergy based on the simple solar exergy equation. Exergy of solar thermal radiation, it has been found that the thermal radiation from the sun is relatively rich in exergy. Bejan presented a unified theory to explain the exergy of solar radiation and clarified the points raised by him in Petela theory described by Petela. Petela expression is used to calculate the exergy of solar radiation extensively at the sun's surface temperature by assuming the sun as a black body radiation source. The equation is the equation now visible to your screen. This is the main equation of solar exergy. The Petela expression for the relative potential of maximum energy available from solar radiation. This is the equation. And the second equation, exergy of solar radiation on the solar collection system for unit area, is obtained with this equation. Exergy of the sun is equal to Gs, where G is the solar radiations, and this factor, this is the Petela expression. And by this equation, this equation you are showing on your screen, this is the most important equation which we have to use for the exergy of any solar systems. Whatever solar energy is incident on the surface of the solar collector or solar pond, and even on the solar photovoltaic cell, the exergy of the sun will be calculated with this equation only, not by the thermal equation. Now this is the basic. Now just I have only now only 30 minutes. Now I wish to explain the calculation part, model part, equation part. So just briefly I am introducing all these things. When we will analyze our solar pond energy as well exergy, so the same schematic diagram, we will use this schematic diagram to analyze the energy and exergy of the solar pond. In our this discussion, I have assumed the basic design parameters of the solar pond. It has been assumed that thickness of the upper convective zone is 0.1 meter, thickness of non-convective zone is 1.6 meter, thickness of heat storage zone is 1 meter, and dimension of the solar pond is 100 into 100 meter. We can frame design different types of solar pond. It may be circular cylindrical solar pond. Here it is of a square shape, 100 meter and 100 meter dimension of the solar pond, and the thickness as you see here 0.1 meter or thickness of the non-convective zone 1.6 meter. We cannot increase the thickness very much. If you will say that you have taken 1.6 meter, I will take 2 meter or 3 meter. No. So there is limitation of keeping the thickness, non-convective zone and heat storage zone, on the basis of there are many factors based on which these thicknesses are taken. And for the analysis, I have taken the typical climatic condition of two locations in India. One is New Delhi and another I have taken for the Bhavnagar, Gujarat. As you know, in the Gujarat there are maximum sunshine, and today our honorable Prime Minister is in the Kutch, and he is going to inaugurate and lead start the solar thermal systems there. And this is the beauty of the Gujarat, where the maximum solar sunshines are available all the maximum time of the year. For the as you know, for any thermodynamic modeling and analysis, you will have to make assumptions. And from the teacher's point of view, if you explain or if you say, if you give any project to any of your students and any of your researchers, so it is very most important thing. So you should ask or you should enumerate, right, what are the assumptions based on which you are going to make the analysis, because without these assumptions you cannot make the analysis. This is the difference between the real theoretical analysis and experimental analysis. In the experimental energy efficiency or exergy efficiency will certainly will be lower than the this theoretical analysis values, because in the theoretical analysis we have assumed so many things. And but you will say, why these two difference, why we should not assume like this. These assumptions are made, and our goal is to achieve the ideality for any researcher or any real working design of any working. We should have one ideal thing, and as an engineer, as a researcher, our aim is to reach towards ideality. Then if we keep such type of things in my mind, then we can improve our systems. Otherwise there will be no improvement in systems. To make our systems improved, we will have to make the ideal system. As a mechanical engineer, you know the Carnot efficiency, though you know the Carnot efficiency cannot be achieved, but it is the ideal efficiency. Or any solar any internal combustion engine cycles, our goal is to achieve to move towards the Carnot, and for which we do so many things. So here in the solar thermal system also, in the solar pond, we have assumed so many things. I am not going to explain it here. I will share it with the coordinator, and you can get this literature. Even all these things which are being explained here, all these facts are published, and you can find on the internet, and many are free, but some papers you are not able to download. I may share my research papers with the coordinator. You can take from him. Even my research papers are also available with your Professor V. Shiva Reddy. You may take from him, and you can go through it all from all those research papers in detail. When we do energy and exergy analysis of the solar thermal system, this flow you are seeing, the transfer, heat transfer, ki how solar energy reaches to the upper convective zone, then non convective zone, then heat storage zone, and so many arrows, and all these arrows, there are some significance, ki how energy is coming, from what quantity is going out, what are the losses, what are the transmissions, or and this is in terms of q. Those energy is in the form of q, and only the if we see the top, there is solar energy incoming, hg. And after that, that solar energy is converted into in the thermal form. So everywhere there is q, and this should be in mind when we analyze the solar exergy, solar thermal systems. So every calculation should not be in terms of q only. It may be in terms of solar radiation, solar exergy. Input energy is solar exergy, and the transmission in the mean, there is thermal energy. So very basic thing. I am emphasizing it because so many researchers do mistake and calculate the single way exergy analysis. This is very important thing, and you should not do this such type of mistake. Whenever you calculate input solar energy, then we should utilize the Patella expression to calculate the solar exergy, and then the simple jo Bejan thermal equation of for the exergy, and Dinsar are very famous name in the field of exergy analysis, Ibrahim Dinsar. You can refer his book also, and my our guide and supervisor, and there will be see their citations of all over country, all over the world. They are citing our papers for their research work, and it is due to the credit goes to our supervisor, Professor S.C. Kaushik, and because it is he, Professor S.C. Kaushik, who has given the emphasis on this difference, exergy calculation, thermal system, and he has categorically utilized and made it public that the exergy of solar energy should be calculated with the expression of the Patella expression, and it is widely accepted all over the world. And now these are the expressions, a lot of expressions here. You will find it in the literature. So I am not going to explain all these things, and it is conversion equations so many equations. Just I am showing you, because without these equations you cannot analyze the system energetically and exergetically. Because to write, one thing you should keep in mind, whenever you are going to analyze any system exergetically, before that you will have to analyze the system energetically. Without energy analysis you cannot do exergy analysis. Exergy analysis is not alone analysis. If someone says that I am doing exergy analysis, it means he has completed an energy analysis. Without energy analysis, exergy analysis cannot be done. So be very careful and be very clear in this fact. In literature there are so many energy analysis. Whatever any system, even in the power plant, or any system, any mechanical system, any thermal system, any even civil engineering systems, even buildings, there are energy analysis. And if there is energy analysis, then you can do exergy analysis. So if you want to do exergy analysis of any system, first of all you do energy analysis of the system, and you know the energy transfer in different parts, different ways, and then calculate the exergy of those energy transfer and put those exergy value in exergy balance equation. Just like energy balance equation, in energy balance there is energy balance equation, you all are familiar. Similarly there is exergy balance equation. In exergy balance equation there is very most important parameter is exergy destruction. In energy balance equation there is no such type of things. There is no energy destruction. Uh, there is no any factor of energy destruction. There is only energy transfer from one form to another. But in the case of exergy destruction, we have to calculate exergy destruction. This is the beauty of the exergy destruction. This is the difference that brings in our analysis. That is not possible through the energy analysis. But if we incorporate exergy analysis, we can calculate, we become able to calculate the exergy destruction, the site of exergy destruction. If we know where is exergy destruction being taking place, where is maximum exergy destruction, then our focus should be on that area, on that sites where we will have to analyze how these exergy destruction can be minimized. If exergy destruction will be minimized, so energy utilization will be maximum. So then energy efficiency will also rise, and then exergy efficiency also rises. If exergy efficiency rises, naturally energy efficiency also rises. So these are the equations. And based on our value, you see a similar type of graph will come after the calculation. Results and discussions here. You see this graph. In the y-axis there are available solar radiation watt per meter square, and on the x-axis depth below top surface of the solar pond. You see, when the upper convective zone, when the depth is 0, if it is in between 300 to 350, you see watt per meter square solar radiation. And in the lower upper convective zone, when it reaches the top of the non-convective zone, it is about 150 watt per meter square. See, if we assume 300 and there is only 150, it means 150 watt per meter square is either absorbed in upper convective zone or reflected. only 150 watt per meter square of the solar thermal energy enter non-convective zone. And here some things goes, and this energy, it reaches to the high heat storage zone at the level of about 60 watt per meter square, and it reaches the bottom, and then heating of the bottom take place. But here there is no convection current. That is why all the heat is stored in this heat storage zone. See here, accounting of the solar energy and exergy of the solar pond. Here I am giving the value of only solar exergy. The solar exergy incident on the horizontal surface, if it is 283.34 watt per meter square. See, this is the solar exergy. Here you are seeing that more than 300 watt per meter square solar radiation, but I am telling you here the incident solar exergy is only 283.3 watt per meter square. Why such difference? This is the difference due to only that Petala expression. The most of the researchers do mistake here. Here they write this 300 watt per meter square, but it will not be 300 watt per meter square. If we that solar radiation, thermal radiation is converted into solar exergy, it will be calculated as 283.34 watt per meter square. This is the basic mistake most of the researchers do when do the solar analysis. And then reflected solar energy from the top surface of the pond is 11.46 watt per meter square, and upper convective zone some absorbed. What is the quantity of absorption? This is there. Then it comes, you come below blackened liner surface is 73.64. This is the exergy here in the blackened liner surface of the bottom. And this is the figure which shows the vertical temperature distribution in the steady state salt gradient solar pond at New Delhi and Bhavnagar, India, without heat extraction. If we do not extract heat from the solar pond, this type of temperature rise take place in the non-convective zone depth from top to bottom. This is the graph you can have after the calculation average temperature of the different zones of the model solar pond located in New Delhi and the Bhavnagar in different months. In the January, this temperature will take the you see the only you see the months May. You see the month May. This is the top surface temperature rises up to about 20 to 25 degrees centigrade. In the upper convective zone, the temperature rises to up to 30 to 35 degrees centigrade, and then non-convective zone, it is up to 70 degrees centigrade, and the heat storage zone is goes between 70 to 80 degrees centigrade in Delhi. But in Bhavnagar, it goes up to more than 80 degrees centigrade in the month of May. Because why this difference? Because in the month of May or in any month, the solar radiation available at Bhavnagar is more than the New Delhi. That is why the temperature of heat storage zone rises more at Bhavnagar. So this figure, this graph has been calculated with the help of our equation, and this equation and the reality is the same. The another this graph energy efficiency of different zones of solar pond you can find here. It is the energy efficiency. I only take the May month. If you see in the month May, the energy efficiency of our assumed solar pond is 33.67% in New Delhi and it is more than 33.67% in May at Bhavnagar. Then you see exergy efficiency of different zones of solar pond. You see exergy efficiency in non-convective zone and heat convective zone both. And then monthly heat is stored in the different zones of solar pond and exergy is stored in different zones of solar pond. Now the most important graph is exergy destruction in different zones of the solar pond. Here you see exergy energy efficiency may be higher, but exergy destruction is more in upper convective zone. This fact is not explained by the energy analysis. The exergy destruction is found to be higher in upper convective zone. So when we do exergy analysis, we find that this is the zone where we should give much attention in designing. Normally, the designer give attention in the design of heat storage zone. But from the exergy analysis, we find that the exergy destruction takes place very high in the upper convective zone. So we should do attention how this exergy destruction can be minimized in upper convective zone. A brief conclusions we may attain, we may get about 96% of the solar energy, incident solar energy, enter the top surface of upper convective zone. About 80% of energy entered is absorbed up to 0.01 meter depth, and next 20 28% of solar energy, and the rest of the 28% is absorbed between 0.01 to 0.1 meter thickness of the upper convective zone, lost to atmosphere convection. Then about 23% is absorbed in non-convective zone and eventually conducted to top upper convective zone and lost to atmosphere. In the similar way, finally you will find that the result of variation of temperature of zones is mainly due to variation in monthly average atmospheric temperature, available solar radiation, radiative humidity, wind speed for a specific thermophysical and design parameters of the solar pond. The highest exergy destruction take place in upper convective zone and lowest in the non-convective zone, which we have seen earlier. This result, the amount of exergy destruction in the form of amount we have calculated, and we have found that overall energy efficiency in or collection efficiency is found to be lower in Delhi as compared to the Bhavnagar. The overall exergy efficiency are 0.32, 1.41 and 0.97. One minute. Yes, this is the annual overall energy and exergy efficiency of solar pond are found to be about 6.46 and 0.9% in Delhi and 7.09 and 1.07% in Bhavnagar respectively. See here, the energy efficiency is about 7%, but exergy efficiency is only 0.9%. See the difference. We should not be happy with the 7% energy efficiency. There is need of attention, because the exergy efficiency is only 0.9%. So there is a lot of the area where we can improve our system so that the exergy efficiency can be increased. So from the research, we have found that there is need to analyze the system exergetically so that we can increase the exergy efficiency as well as the energy efficiency. Now, the another part, since we are moving towards the end, so similarly, there are calculations for the solar distillation systems, passive solar distillation system. In the same way as we have explained in the solar pond, there are energy equations. See this figure of solar steel, how the solar energy comes. For all the heat transfer, there are the values, and based on all these value, energy equations are written, and for those energy equations, there we calculate the exergy equations and then find the exergy distribution of different parts, and by the calculation of exergy distribution, then we can suggest the ways of the exergy improvement, energy efficiency. See, this is the all heat transfer equations for the passive solar steel. So based on this heat transfer, we can model our exergy model of the passive solar steel. These are the different equations you can find in my papers, and then we can calculate the exergy efficiency of glass cover and the overall solar steel. And then there is the exergy equations, and based on these exergy equation, we can calculate. And then I just only share one most important results. Numerical results obtained by the energy and exergy analysis are in good agreement with the result published with respect to the effect of design and climatic parameters on productivity and energy efficiency of the passive solar steel. It has been observed that the most prominent parameter is solar radiation incident on the solar steel. Productivity of a passive solar steel increases with the increase in the amount of incident solar radiation. So these are the different types of graphs of the energy and exergy, that the heat transfer at different parts of the solar steel, and you can calculate these are the graphs you will have to make, you will have to calculate, and your student will have to learn how to come to these graphs, because graphs only speaks in your research papers. The researchers find the graphs based on your calculations, because the calculations whatever you do are not given in the research papers. It is reflected through your graph and these conclusions. As the one participant was asking about the value of the distillate output, it is estimated that maximum global energy efficiency of the solar passive steel will lie in the range of 33 to 67%. Then it is heat losses, then exergy efficiency, and then here you find it is observed that highest exergy is distributed in basin liner. As far as the solar steel is concerned, the highest exergy destruction take place in the basin liner. In the solar pond, you have found that the highest exergy destruction takes place in upper convective zone, but in case of solar steel, the highest exergy destruction takes place in basin liner and lowest in the glass cover, corresponding to the total solar exergy input on a typical day. So as a designer, our emphasis will be on the design of the basin liner, because the maximum destruction takes place at the basin liner. Through energy analysis, we cannot come at this conclusion. Through energy analysis, we cannot say like this, okay, basin liner, there is need to improvement much. And the unit cost of desalination, I have calculated, and it has been found to 1.9 rupees, 1.9 per liter through this passive solar systems. It may be possible by reducing the exergy destruction in components with or without marginal increment in capital cost of passive solar steel. Then after that, there is the new models in which the solar steel is combined with the solar pond, that is the active solar distillation system. With this active solar distillation system, these are the equations. You may not be interested very much. All the participants, one who is will be interested will get from the coordinator. I will share all these things with him, and these are the figures. And see, this is the overall energy efficiency and productivity. See here, the productivity is calculated in the units liter per meter square per day. When thermal energy input is 0, see, when thermal energy input is 0, even though there is productivity. How? Because the energy comes from the solar pond, and during the daytime there is thermal energy input, so the total energy in the solar steel will be higher, and due to that the productivity will rise, and it can be up to 16 liter per meter square per day in the case of active case. In case of active solar distillation, 16 liter per meter square per day can be achieved, the the output of the solar distillation systems. So these are the lists of my publication available on the internet, and since time is over now, I would like to thank you for your patient hearing. Thank you, Dr. Reddy.
Yeah, thank you,
Dr.
sir.
Please, because due to time limitation, there are so many things to be shared, but 2 hours time is found to be very less.
Okay, sir. Any questions from the participants?
Yes, yes.
Any questions from the participants? Please unmute yourself. Any questions from the participants?
Actually, I have taken much time, so due to this much time, then there is no question.
No questions. Okay, sir. No questions from the participants. So thank you, sir, for your valuable and quite informative session. on the exergetic analysis of solar pond and desalination. So this may be useful for the participants. So to do the research in the exergetic analysis. So thank you, sir. Thank you, sir, once again for giving.
Thank you, Dr. Reddy.
Yeah, thank you,
And
sir.
because there are so many Reddy, so I will say Dr. B. Siddha Reddy, Dr. V. Siva Reddy, and
Oh.
other Reddys also. And I am very thankful to you also. You have heard, you are present throughout the session, and
Yes.
you have helped me in the different ways. So I am very much thankful to you, Dr. B. Siddha Reddy.
Yeah, please, sir. Welcome.
Thank you, thank you, thank you.
So thank you.
I will share the PPT with you,
Okay,
and
sir.
you can give the interested participant who need it.
Okay, sir.
Okay, thank you, thank you.
Okay, sir. Please.
Anything more? Anything more you want to ask me?
Yeah, nothing, sir. So you can leave, sir.
Okay, okay, thank you.
Okay. So, dear participants, this ends the second session. So tomorrow we'll meet you again at 10:30 a.m. So we have the session by Dr. S.K. Tyagi, Associate Professor, IIT Delhi Center for Energy Studies, on the topic clean combustion and biomass cookstove. So thank you. So this session is